When it is balanced, we have no voltage here. If it will change, we will receive voltage here, 168.69 millivolts. When we will take the other side movement, at that time the same load will cause to change the voltage here. Now it is 169 negative millivolts. In one direction it is positive, the second direction it will come negative. Assalamu alaikum wa rahmatullahi wa barakatuh. In my last video number 641, while discussing how we can test a load cell, I demonstrated that the input resistance is 397 ohms, that is 400 plus minus 10 ohms, and the output resistance of this load cell is 350 ohms. And I received comments that explain the function of this load cell, how it works. Let's start. Basically, load cell is 4 resistors configured in Wheatstone Bridge in a bridge shape. They are balanced resistors, equal resistors. Let me select resistors and then I will explain it. We will consider 590.4 ohms. This is including the multimeter error. 590.4 ohms. 590.4. 590.1 ohm. And this one 590 ohm. This time we have 4 resistors here. If I will connect them together in this configuration, so these are in bridge shape. It is called Wheatstone Bridge. We can say this is R1, this is R2, R3, R4. When all resistors are in same resistor value, every resistor is in equal value, we can say from this point to this point, if it is input terminal, these are output terminals, and if we simplify it, this circuit, this is our one resistor set and this is second resistor set. Look from this point, one resistor, second resistor. And we make an output point here. So these are 2 resistors in series, 2 resistors in series, 2 resistors in series with 2 resistors in parallel, the other set. So we can say we have 2 different paths of electrical current. If we connect here a battery, positive, negative, the current will flow from here and here. If the resistors are in same value, R1, R2, R3, R4, the branch current in this resistor and branch current in this resistor set will equal when all resistors are equal. In our case, if it is 590 ohm, if it is 590 ohm, 590. So we can say at this point, we will say it is I1, current number 1, and I2. I1 is equal to V R1 plus R2. If you apply 5 volt here, R1 590 ohms plus 590.4 plus 590.4, so it is 0.00423, 0.00423 ohms. And in this side here is 590.1. The same current will flow here because there is a minor change in the resistor, so we can consider these are the same. If the resistors are in the same value, when the current will flow from this point to this point and in this channel, and voltage drop across each resistor will equal. So voltage at this point, voltage at this point will equal. If the value of any resistor will increase or decrease, any one resistor, three are stable, any one resistor is changed, what will happen? It will cause to increase the channel current in this side and in this side. If you connect some load, some galvanometer here, that will show the current. For example, if resistors are equal, that's okay. Now we can calculate the voltage value at this point and at this point. So this is our branch current. If we calculate the voltage value at this node, multiply with 590 ohms, so 2.498 VR1, that is R1 I1. So this is I1, so it is 2.4989 volt. And if we see here in this point, the minor change here, it is 2.499 VR3, 2.4993. Now here is change in the millivolt. It is 4989 and here is 4993. So this change in one resistor will cause to unbalance this bridge configuration. Let's understand with some easy example. I have a water pipeline from here that is 4 inches diameter. At this node, if I connect this pipe 2 inch from this side, 2 inches, and then I connect 2 inches here pipe, and this one 2 inches, and exit 4 inches, and we make another pipe connection joint here between these two. Now what will happen? The water will flow here and it will divide it into two portions, here, here, here and here. This time, because the pressure at this joint is equal, now no water will flow here. The water will flow in this path and in this path. If we close this diameter, this pipe, we close it. Here we can say 1.5 inches. Now the water flow will disturb. Here is 2 inches, but here we increase the resistance. So water will face resistance, pressure will increase here. This time the water flow from this path will increase. Why? In this channel we have resistance. So pressure at this point will cause to divert the flow in this direction as well. Because here is 1.5 inches now. So it will cause to deliver the water in this side. In the second condition, if we open this pipe, we can say 3 inches. This time the water will flow from this point to this point similar, but here it is 2 inches, here it is 3 inches. Now it will cause to decrease the pressure here, drop the pressure here, and it will cause to suck more water in this channel. Before this, when the pressure was increased by increasing resistance, the water flow was in this direction. Now when we open the dia, the water started to flow in this direction. So this unbalancing, increased or decreased resistor will cause to increase or decrease the pressure here. If we will increase resistor, here we will take positive pressure, so it will cause to flow the water here. The similar here, this example to understand this. If all resistors are equal in the resistance, at that time we will take the same current flow here. But if we have some unbalanced resistance, it will cause to increase current flow here. Let's check it practically. Now I applied 5 volts to this bridge, Wheatstone Bridge. From this point to this point I applied 5 volts. And let's check how much voltage are here. It is 0.01 millivolt. Move to millivolt. So it is 0.39387 millivolt. Why? Because one resistor is slightly high. Okay, let's unbalance it, because here in this side we have 590.4 ohm resistor, so we will change the direction now. Let's measure the voltage here. We can see we swapped the resistance, now there is unbalance. Now I will add some variable resistor to understand its function. This bridge configuration, it is named as Wheatstone Bridge. So it is 0.29 millivolt. Difference between this point A and point B. We can say it is the input voltage, these are the excitation voltage, and this is output of the load cell. These 2 points are the output of the load cell. Now I will use this resistor as our Rx in place of R2 or any one resistor, and we will unbalance this resistor. Okay, 590 ohms. We will increase or decrease this resistor and we will check the results. This time we have 8.9 millivolt change. Now if this resistance will increase or decrease, I am rotating it clockwise, the voltage increased. Now if resistance will decrease, we can say here we have just only 1.3 millivolt. It is 0.0056. That means this time the bridge is balanced. The Wheatstone Bridge is balanced. This time we have very closer to 0. If we have some precisely adjustable resistance, that will make it dead zero. That time this bridge will balanced. Now come to this point. This resistor, these are balanced resistors, just only one resistor is now variable. In this load cell there is metallic wire that is very thin wire, that is 1 thou, 1 over 1000 inch, that is 1 thou wire, most of the time copper nickel alloy, that is wound in the grid form. When it is moving in this way, compressed, or when it has some stress here between this point and this point, what will happen? Its metal will slightly take stress. So this stress will cause to increase or decrease the resistance of this material here. Here it have 4 resistors. In some load cells there are 4 resistors, the similar copper nickel wires that are precisely adjusted with the accurate resistance. When this have no load, when it have no pressure on this point, at that time it will become balance. When it will take some pressure here, we will apply some pressure here, it will cause to change the resistor here, and that will cause to give output voltage. If it is in one side, it will give positive voltage. We can say 16 millivolt. Now I will decrease the resistance. When the resistance is decreasing in the other side, the voltage are going in minus. So this is the function of this load cell Wheatstone bridge. In some load cells, it is using 4 resistors. When it have no pressure, all the resistor will balance. Same resistor value. When we will apply pressure, for example, we are giving some tension, stress, at that time this resistor and this resistor will change its value. When it will take strain, the other 2 resistors will change its value. So this changing value will cause to determine which direction of force is applied. Now make it 0. When it have 0, 0 output, 0.00, so that is precisely balanced. Now the next question, when we say the output resistance is 350 ohms in these 40 kg load cells, class 3 load cells. Some of the load cells have more resistance, that is 700 ohms. We can say this is the output point and this is the output point. We can say this is the output point, 590 ohms. Why? Because we are using 590 ohms. We can calculate it. 590 plus 590 multiply with 590. This is 590.4. 590.1 plus 590.4 divided with 590 plus 590.4, that is R1 R2, plus 590.1 plus 590.4. So it is 590.02 ohm resistor, that is exactly here. 590 ohms resistor. This bridge configuration is giving a resistor with these resistors and with these resistors. Why? Because we are taking R1 R3 in series, R2 R4 in series with parallel to each other. Now we can say it have input resistance 590 ohms, but when we connect it to excite it, to give excitation for safety purpose, a current limit resistor and balancing resistor is connected here. I connected 1 kilo ohm resistor here, 1 kilo ohm resistor here, but if we see from this point to this point, this point to this point, these resistors have no effect. But if we connect between these terminals, Now it is giving 2.561 kilo ohm. Why? Because we have 1 kilo ohm resistor in series with 590. So this series parallel combination will cause to increase the input resistance. So here we have high input resistance, low output resistance. So it is configuration of a load cell. It is configuration of Wheatstone Bridge. Anytime when we apply voltage here at this point and this point, and we have unbalance in any one resistor. For example, we decrease this resistance. Now it is 169 millivolt. It is one direction movement. I connected this resistor in parallel. This voltage dropped. And if you decrease this resistance, if you will change this resistance, the voltage will cause to increase because this time it is in positive. Here it is in negative. Here in positive. If this resistor will decrease, the voltage will drop in negative side. This end become positive, this end become negative. The potential here is now 169 millivolt. And if you decrease this resistance, it will cause to increase the voltage. So it will cause to determine the direction of the load. Either the load is increasing or decreasing. So the unbalance in the stress gauge here or strain gauge here. So the pressure on this load cell will determine the resistor of stress gauge, strain gauge, and that will cause to change its resistance, and we will take equivalent voltage to the load that will correlate the load in form of voltage. So we will receive that voltage here at these terminals. When it is balanced, we have no voltage here. If it will change, we will receive voltage here 168 with 69 millivolts. When we will take the other side movement, at that time the same load will cause to change the voltage here. Now it is 169 negative millivolts. In one direction it is positive, the second direction it will come negative. So these two resistors will used as a compressive load. When we will apply stress, it will measure the stress. When we will apply strain, at that time it will give the voltage direction in negative or positive. I hope so this video is informative. If it is informative, hit the like button. If you have any question, let me know in the comment box. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.